Hi, welcome back. This time we're going to talk about another application of double integrals, and this time we're going to talk about two-dimensional probability density functions. Um, so in this example, we're going to talk about continuous probability distributions. But to motivate that, what I'd like to do first is talk about some discrete probability distributions. So let's imagine a professional archer. So here's our archer. They are shooting their arrows over in this direction. I should put my arrow that way. They're shooting their arrows, and what they're going to do is they're going to aim for this target. And what I first want to do is talk about a rectangular target. So we have here a rectangular target. It'd be better if we had some straight lines, but we're super wiggly. All right, I'm going to color in some of these regions. All right, we like red for the middle, and then we'll put some yellow on the outside. All right, so here is our professional archer. They're aiming for the target. The target is a square, and we can make up, this person knows how to shoot their arrows, and let's make some assumptions about where the arrows hit with what probabilities. All right, so let's say when they aim for the target, they always hit the target, but they hit the bullseye, which is that center spot, that red part, 40% of the time. They hit each blue square 10% of the time. And each yellow square 5% of the time. So we could put these numbers in here, 0.4, 0.1, 0.1, 0.1, 0.1, 0.05, 0.05, 0.05, 0.05. So this is the likelihood that the arrow ends up in each of these different squares in the target. So note, and this is a really important part in any probability question, note that these numbers add up to 100%, to 1, or consider that to be 100%. And that's going to be the case always in probability questions, right? So 0.4 plus 4 times 0.1 plus 4 times 0.05 is indeed equal to 1. So when we're in this situation, we can ask questions. Why do we have a square target? Why does the archer always hit the target? Why is it only 40% of the time? Hey, I'm making up as I go along. So we can ask questions like, what is the probability that the archer hits one of the boxes on the right third of the board? So if I'm going to draw this question, what I'm asking is, what's the probability that the archer hits one of these three parts of the target? Well, with this discrete probability, what we can do is we can just add up those numbers. Add up the discrete probabilities for the for these boxes, and we get, so 0.1 plus 0.05 plus 0.1, which is, oops, what am I doing? Plus 0.05 again, and we get 20%. So 20% chance that the archer hits that side of the board. So that's when we're dealing with discrete probabilities. We can just add up those values. All right, so now we're going to bring our archer down here, and we're going to change the board for them. All right, let's bring this person over here. Over here, blank. Paste our archer here, but this time the board isn't going to be a square. The board's going to have a circle, and there's not going to be any marks on it. Well, you can imagine that as the archer shoots and aims for the points on the board, the archer is much more likely to be near the center of the board, but you might expect that the points about where all the arrows lie is going to spread out, and it's going to be more clustered around the center, but there'll still be some arrows that happen outside the center. So, so now consider a circular target. With no markings. All right, where the archer aims for the center. So with no markings, so with no boxes, each arrow hits a point. And if you looked at the density of the arrows, it would be bunched towards the center. With the density decreasing as you moved out from the center. Of the target. All right, so if you think about it, the probability that you hit any one point is basically 0, because hitting exactly one point, you're just not going to do that with any regularity. But even though the probability that any one point has 0 probability, some points are more likely than others. So even though there is 0 chance of hitting any one point, some points are more likely than others. All right, and so what we get is we get a function about how likely it is that an arrow hits in a region. And so if we were to take this picture, this circle, and turn it on its side, what we'd see is maybe something like a bell curve, a three-dimensional bell curve, where you've got a more likely chance to hit in the middle and a less likely chance to hit on the side. So this is called a probability density function, the original kind of PDF, and can be seen as a function f of xy over a domain D. And one thing that makes it a probability density function is this idea that we had earlier. We must have that the integral over this domain of f of xy dA is equal to 1. That's a key part of being a probability the density function. So this is the same thing as saying the total probability of any event occurring is 100%, is 1. All right, and so you can calculate the probability that any subregion is hit by the archer by integrating over it. So if we have this bullseye, and if we have this domain, and then we put a bullseye on the chart, we can say, so a question that we can answer is, given a probability density function f of xy, what is the likelihood that the archer hits the bullseye? We call that b, and then we would say, oh, well, the integral, it would be the integral of f of xy dA over b. So just like before, we were talking about summing up all the regions that gave us the probability of the discrete probability. Here, when we have a continuous variable, a continuous probability density function, we have to integrate over this subregion. We don't even have to divide by the total area because we know that the probability of any event occurring is 1. All right, so let's stop there. I'll come back with a couple more examples of applications of these double integrals. See you soon.